So, Assalamu alaikum. Our topic today is going to be based on Form 2 work. That's the effects of electric current on substances. So, before we start with the topic, let's first check on those substances that can be able to conduct electricity. We have the conductors and the non-conductors. So, we have those substances that conduct electricity are referred to as conductors, while those that do not conduct electricity are referred to as non-conductors. So when we are going to check under the electrical conductivity on substances, we are going to check electrical conductivity on solids, electrical conductivity on molten substances, and electrical conductivity in liquids. So we first check on electrical conductivity in solids. So when checking the electrical conductivity in solids, we have those solids that conduct electricity and those ones that do not conduct electricity. So you will find that metals are good conductors of electricity, and graphite is also a non-metal which conduct electricity. The reason why these substances conduct electricity, when talk about metals and graphite, it is because of the localized electrons. While those substances that do not conduct electricity do not have the localized electrons when solid state, therefore they do not conduct electricity. And when carrying out electrical conductivity in solids, the apparatus needs to be arranged in such a way that, for example, we can put the cell here, where that's our cell. Then we put our bulb there. Then at the point here, we can put a crocodile clip. So what is going to happen? The substance to be tested is supposed to be placed at that junction there. If you find that the bulb is lighting, that means that that solid is a good conductor of electricity. And we have said that those substances that conduct electricity is due to the presence of the localized electrons. So metals and graphite conducts electricity when in solid state due to presence of the localized electron, due to presence of the localized electrons. So that's the reason why metals are good conductors of electricity, and graphite is also a good conductor of electricity. Substances like wood, we have glass, we have rubber, we have plastic. Those ones do not conduct electricity. We also have sulfur. So this is because these are molecular substances and they lack the localized electrons. So we have here, we have glass, wood, we have rubber. Rubber are poor conductors. Rubber are poor conductors due to lack of the localized electrons. So that is the electrical conductivity in solids. Now the second step is going to be electrical conductivity of molten substances. So we have electrical conductivity in molten substances. Talk about molten substances. So when talking about electrical conductivity of molten substances, you will find that there are some of the substances, when they are in solid state, they don't conduct electricity. When they are in molten state, they conduct electricity. And there are also those others that you will find that they will be good conductors of electricity both in solid state and in molten state. So when carrying out the test for electrical conductivity of substances that are in molten state, the apparatus or the experiment should be carried in a way that the apparatus are arranged like this. So we have this one here. We put our bulb there. This one comes like this. So we have the substance to be tested. Then here we have the switch, we have the bulb, and we have the cell. This one is source of heat. The function for the source of heat is to melt the solid substance. So we are going to put the substance to be tested at this point. You will find that metals will conduct electricity both in solid state and in molten state, which means that if I place a metal here and I heat it to melt, then I carry out the electrical conductivity, it will still conduct electricity. Reason being, it will still use the delocalized electrons in electrical conductivity. So the first one, A, we talk about metals conducts electricity when in molten state, because of delocalized electrons. So I have delocalized electrons, therefore they will conduct electricity. Then B, we can also have ionic compounds. Ionic compounds, we have salts and we have bases. They will conduct electricity when in molten state. This is due to the presence of free or mobile ions. So we say the second substances which conduct electricity when in molten state are ionic compounds. So ionic compounds conducts electricity when in molten state because of mobile ions. So examples of the ionic compounds, example of ionic compounds are, we have salts and bases. Salts and bases. For example, I have sodium chloride. I also have magnesium oxide. This one here is a base, while this one here is a salt. Sodium chloride will conduct electricity when in molten state. Magnesium oxide also conduct electricity when in molten state. But in solid state, you find that ionic compounds are poor conductor of electricity. This is because the ions are at fixed position and therefore cannot be able to move about to conduct electricity. So that is how we distinguish between ionic compounds and metals. So ionic compounds are only good conductors of electricity when they are in molten state and in solution state. But when it comes to metals metals conduct electricity both in solid and in molten state. So the difference in terms of electrical conductivity, you find that metals uses the localized electrons, while ionic compounds uses mobile ions or free ions. And the third part, we have looked at electrical conductivity in solids, electrical conductivity in molten substances, and now the third part is electrical conductivity in solutions. So solutions or aqueous substances. When it comes to electrical conductivity of aqueous substances or substances which are in solution state, the apparatus will be arranged the same way. This one here is switch. So we are going to have our cell here, then we connect it, and this one we have our bulb. So that is the arrangement of the apparatus. So we have this one here as the bulb, that is the cell, and we have the switch. So what happens is the solution to be tested is placed inside here, and there are rods which are being dipped inside the solution. At the same time, the substance that was being tested when in molten state, there are rods which are being dipped inside the solution. These two rods that are being used must be good electrical conductors. They must be conductors of electricity for continuous flow of current for the bulb to light. So if you see the bulb lighting, meaning that that substance is a good conductor of electricity. And if the bulb does not light, then that substance is not a good conductor of electricity. So in solution state, you will find that those substances that conduct electricity when in solution state are salts, we have acids, and we have bases. While molecular substances like sugar, when in solution or even in molten state, they do not conduct electricity. This is because they lack mobile ions. They lack mobile ions. At the same time, they do not have the localized electrons. So we are going to say that in solution state, those substances that conduct electricity include the ionic substances, e.g., we have acids, we also have bases, and we have salts. The reason why they conduct electricity when they are in that state is because of mobile ions. So solution substances that conduct electricity when in solution state are: one, we have salts; two, we have acids; and three, we have bases. So these substances are conducting electricity when in solution state because of mobile or free ions. So they have mobile stroke free ions. For example, I have here hydrochloric acid. Hydrochloric acid in solution state will contain hydrogen ions. We have chloride ions. We have the hydroxide ions, which is the OH negative. So something which is in solution state means it contains water. When water is ionizing, it ionizes to give hydrogen ions and hydroxide ions. That's why the hydrochloric acid here contains the hydrogen ions, sodium chloride ions, and the OH ions. I also have sodium chloride aqueous. This one here is a salt, while this one here is an acid. When sodium chloride is dissolved in water, it ionizes to give sodium ions. We have chloride ions. we have hydroxide ions from water, and we also have hydrogen ions. These are the ions which are responsible for electrical conductivity when it comes to sodium chloride, which is a salt in solution state. Then example of a base, I can also have potassium hydroxide in solution state. So if I have here potassium hydroxide, which is a base, I'm going to have potassium ions, we have hydroxide ions, and we have hydrogen ions. So due to these, mobile ions makes these substances which are in solution state to conduct electricity. Then a point to note is that under our NB is that molecular substances do not conduct electricity both in solution and in solid state or even in molten state. This is because they lack mobile ions. At the same time, they also lack delocalized electrons. So we say molecular substances do not conduct electricity when in solid, molten, or solution state due to lack of free mobile ions or delocalized electrons. Examples of the molecular substances that we are having, we can talk of sugar. Sugar is an example of a molecular substance. So when you put it in molten state, it will be a poor conductor of electricity. If you dissolve it in water, again, it will not conduct electricity. We can also have sulfur as another example of a molecular substance. Sulfur is also an example of a molecular substance. So we have many molecular substances. So as long as that substance is a molecular substance, it will not be a good conductor of electricity. Now, we are having hydrochloric acid. This one will conduct electricity when in solution state. But what of hydrogen chloride gas? Hydrogen chloride gas, if liquefied to be in liquid state, it will be a molecular substance. Therefore, it will not contain mobile ions and cannot conduct electricity. So it only conducts electricity when it is dissolved in water, where it is going to ionize to give the ions, making it to be a good conductor of electricity. Then now, the next part of this so we have what we call electrodes. When we were carrying out electrical conductivity of molten substances and solutions, there are two rods which are dipped inside the substance to be tested. Those rods are referred to as electrodes. They are referred to as electrodes. Electrodes are of two types. We have the anode electrode and the cathode electrode. The electrodes are connected to the cell. We have that electrode connected to the positive terminal of the cell is referred to as the anode, while the other one connected to the negative side of the cell is referred to as the cathode. So we have said that the rods connected to the cell are referred to as electrodes. We call them the electrodes, and we have said that electrodes are of two types. Electrodes are of two types. So we have types of electrodes. So one, we have the anode electrode. Anode electrode. Anode electrode is the electrode connected to the positive terminal of the cell. So we say electrode connected to the terminal, connected to the positive terminal of the cell, connected to the positive terminal of the cell. Then we have the second one, which is the cathode. Cathode is the electrode, cathode electrode. So is the electrode connected to the negative terminal of the cell, connected to the positive terminal of the cell. So if we have the arrangement, we have this one here. So we have the substance being tested. In that, we have this one here. This one is switch. That one is the switch. We have here our bulb. So the longer, if we have the representation of the cell in such a way, the longer bar represents the positive terminal, while the shorter one represents the negative terminal. Therefore, the electrode connected to the negative side of the cell is referred to as the cathode. This one is the cathode, while the one connected to the positive side of the terminal of the cell is known as the anode. So, and here is the substance tested. The substance tested, and we have heat. And we have already said that the function of heat is to melt that substance that is tested. Because we have seen that ionic substances will conduct electricity when in molten state or in solution state because of mobile ions. In solid state, they will not be able to conduct electricity. Therefore, you will not see this bulb here lighting up. And the reason is the ions are at fixed position. Therefore, that's the reason why we need this heat. Meaning, if you omit the heat and the substance is in solid state, whether it is an ionic compound, it will not be able to conduct electricity. So that gives us the importance of the heat for the process to occur efficiently or the bulb to light. Now, I want us to check what happens during electrical conductivity of ionic substances when in molten state. Ionic substances, when in molten state, they contain one anion and one cation. Those substances that condense one anion and one cation in molten state, they are referred to as binary electrolytes. We call them the binary electrolytes. So we are going to find that so the process of decomposing electrolyte. The process of decomposing electrolyte by passing electric current through it is referred to as electrolysis. We call it electrolysis. And what is electrolyte? What is this electrolyte that we have talked about? Electrolyte. So we say here electrolyte. Electrolyte is defined as any substance which conducts electricity when in molten or in solution state and gets decomposed. any substance that conducts electricity when in molten or in solution state and gets decomposed. Remember, metals when in molten state are conductors of electricity, but they do not get decomposed. Therefore, they are not electrolyte. They are not electrolyte. For a substance to qualify to be called an electrolyte, it must conduct electricity when in molten and solution state and gets decomposed. So we say electrolyte is any substance which conducts electricity, when in molten or solution state and gets decomposed. So it must get decomposed. So our topic today is under electrolysis. It's mainly going to be based on binary electrolytes. So we say those electrolytes that contains one anion and cation are referred to as binary electrolytes. We call them binary electrolytes. And mainly are ionic compounds when in molten state. Example, I have sodium chloride in molten state. Sodium chloride in molten state, I'm going to have sodium ions and the chloride ions only. So we call this one as a binary electrolyte. It contains sodium ions and chloride ions. I can also have magnesium oxide in molten state. The ions present are going to be magnesium ions and the oxide ions. So you can see, and the oxide ions. So the ions present is only two. We have the magnesium ions and the oxide ion. Therefore, such kind of an electrolyte is referred to as a binary electrolyte. Then the electrolytes that contains more than two ions, more than one anion and cation, are referred to as non-binary electrolyte. And non-binary electrolytes are mainly in solution state. For example, let's compare sodium chloride in solution state and sodium chloride in molten state. If you look at sodium chloride, when in solution state, it contains sodium ions, chloride ions, hydroxide ions, and the hydrogen ions. Hydroxide ions and the hydrogen ions are from the ionization of water. While when in molten state, we have sodium ions and the chloride ions only. Therefore, this one is referred to as the binary electrolyte, while this one is referred to as non-binary electrolyte. So during the process of electrolysis, when you are passing electric current through an electrolyte, we have what we call anode reaction and the cathode reaction. What do we mean by anode reaction and the cathode reaction? There are some of reactions that are going to take place resulting into the decomposition of the electrolyte that we are having there. So, for example, let's have a look at electrolysis of molten lead-2 bromide. Electrolysis of molten lead-2 bromide. So we have said that during electrolysis, we have the anions and the cations. Anions migrate towards the anode, while cations migrate towards the cathode. Anions are the negatively charged ions, while cations are the positively charged ions. So we take a note that during electrolysis, anions anions migrates towards the anode, and gets discharged, while cations migrates towards cathode, and gets discharged. So that is what happens during the process of electrolysis. Example is electrolysis of molten lead-2 bromide. Example, electrolysis of molten lead-2 bromide. Electrolysis of molten lead-2 bromide. Lead-2 bromide in molten state, we are still going to have the same diagram. So we have this one here as the cell, and we have this. So we have lead-2 bromide here, Pb, Br2 in liquid state. We have that one there is our bulb. This one here is the cell. We have the switch. We have that one as the switch. So this one here represents the anode, and this one represents the cathode. So we have the ions that are going to be present in this this substance is the lead ions and the bromide ions. Now let's have a look at the anode half reaction and the cathode half reaction when electric current is passed through molten lead-2 bromide. So during the process, you will find that the lead ions, which are positively charged, migrate towards the cathode, which is the negative electrode, while bromide ions, which are negatively charged, migrate towards the anode, which is the positive electrode. Just the same as the law of magnetism. Like poles repels while unlike poles attract. So we have the anode half reaction. So bromide ions will be attracted towards this electrode and gets discharged. So we have bromide ions, which is Br negative, gets attracted towards this electrode, and gets discharged. And how are they going to get discharged? Bromide ions are normally negatively charged, so they form an ion by gaining electrons. Now, for grass to get the molecules of the bromine, they must lose the electrons gained. Therefore, the equation of the reaction is going to be Br negative, which is in molten state. Substances in molten state are in liquid state. Therefore, their state symbol is liquid, meaning that now we are going to get bromine molecules. Because bromine is a halogen and they are diatomic, we balance here by putting 2 plus a total of 2 electrons. One bromide ion loses 1 electron, so 2 bromide ions loses a total of 2 electrons. And the color of bromine, here we are going to observe brown or red-brown gas. We have red-brown fumes are going to be observed, meaning that for you to know the observation that is going to be made at the anode or the cathode, you must know the equation of the reaction occurring at the anode or the cathode. Like in this one here, we have said that the bromide ions are going to be discharged, and we are discharging the bromide ions. 2 electrons were going to be lost, forming bromine molecules, and the color of bromine molecules is red-brown. Therefore, the observation made at the anode is going to be red-brown fumes, or red-brown gas is going to be formed at the anode. Then we have the cathode half reaction. We have cathode half reaction. At the cathode, which ions migrate towards the cathode? The lead ions, which are positively charged ions. So we find that lead 2 ions migrates towards the cathode, and gets discharged. They get discharged by gaining electrons. The charge on the ion tells you the number of electrons that ion needs to gain or lose for it to get back to atoms. So if you look at the lead 2 ions, we have Pb2 positive in molten state. The charge is positive 2, therefore that tells us that we need the lead ion to gain 2 electrons to get back to lead atoms. So this one is going to be plus the 2 electrons, giving us Pb in solid state. And the color of lead is gray. So the observation made towards the cathode electrode is gray beads will be observed towards the cathode. Gray beads are going to be observed towards the cathode. So the overall equation, you can see now the equation is going to take place as electrons are being lost towards the anode. The same electrons are going to be gained towards the cathode. So anode is the electrode where there is going to be losing of electrons, and losing of electrons is referred to as oxidation, while at the cathode is gaining of electrons, and that is referred to as reduction. If we may also look electrolysis of magnesium oxide in molten state. What happens when we carry out electrolysis of magnesium oxide? First, you need to know the ions that are present in that electrolyte. From the name molten magnesium oxide, we are going to have magnesium ion and oxide ion. Oxide is from oxygen when in ion. So we are going to have electrolysis of molten magnesium oxide. Electrolysis of molten magnesium oxide. So the ions which are present here, ions present is magnesium ions and the oxide ion. Those are the ions that are present in that electrolyte. So one of them will migrate towards the anode and the other one migrates towards the cathode. Which one migrates towards the anode? Anode is the positive electrode, therefore oxide migrates towards the anode, while the cathode, which is the negative electrode, magnesium ions migrate towards the cathode. Therefore we have the anode half reaction. Anode half reaction, as we have said that oxide ions migrate towards the anode and get discharged, and they will be discharged by losing electron. So we have O2 negative giving us O plus the 2 electrons. So we know that oxygen is diatomic. A molecule of oxygen is made of 2 atoms. So we need to put here 2, which is gas, and 1 oxygen loses 2 electrons, but we have got now 2 oxygen there, we balance. So we multiply how many electrons will be lost. This gives us a total of now 4 electrons. 4 electrons. So this is going to be the equation that's going to take place towards the anode. Now in this reaction, there is no observation you can make since oxygen is a colorless gas, so you can't make an observation over something which is colorless. So no observation is going to be made towards the anode. But when we come to cathode half reaction, we have the cathode half reaction. Cathode half reaction. At the cathode, magnesium ions migrate towards the cathode because we have said that cathode is the negative electron. Therefore, we are going to have the magnesium ions. From the charge on the ion tells us the number of electrons that ion needs to gain for it to get back to atom. It has a charge of positive 2, therefore it will gain 2 electrons. So here we are going to have plus the 2 electrons giving us magnesium in liquid state. So on the anode electrode, the color of magnesium is gray. So again, some gray beads will be observed towards the cathode, while towards the cathode, towards the anode, no observation is made since oxygen is colorless. So that explains what happens during electrolysis on both anode electrode and the cathode electrode when carrying out electrolysis of molten substances. Now, what are some of the applications of electrolysis? Applications of electrolysis. So we have application of electrolysis in daily life. Where do we apply electrolysis, or where does the knowledge of electrolysis being used? That's what we mean by applications of electrolysis. One application of electrolysis, the first one, so we have applications. Application of electrolysis. Electrolysis. The first one, we apply electrolysis in extraction of metals. One is extraction of metals. Extraction of metals. E.g., we have sodium and aluminium. Sodium and aluminium. So sodium and aluminium are very reactive metals which cannot be extracted by use of reduction. But these ones we use electrolysis in their extraction. Number two, purification. Purification of metals. Purification of metals. Purification of metals. When it comes to purification of metals, this one is going to be checked into details when it comes to extraction of metals. That is in Form 4 work. And during extraction of metals, you will find that the impure metal is made is placed at the as the anode electrode, while a pure strip is placed as the cathode. Therefore, during the process, the anode electrode will be wearing out, giving the ions of the metal that is being purified, and that the ions of the metal will be discharged towards the cathode and will be obtained when it is in a pure state. So that is the purification of metals. While the third one is electroplating. Electroplating. Electroplating of metals. When we are carrying out electroplating of metals, this one is for beautification. Electroplating is being done for beautification. Apart from beautification, also to prevent corrosion or rusting. To prevent corrosion or rusting. For example, we have the curtain bars in our houses. You can check that curtain bar around your house. You will find that it looks more like gold, but it is not gold, or silver. If you scratch it, you will find that that layer of gold or silver is coming off. That indicates that that curtain bar was electroplated using gold or using silver. That was to prevent it from corrosion or rusting, and also to make it more attractive or more beautiful. So this gives us some of the uses. And the last part, which is the use application of electrolysis, is for manufacture of pure chemicals. In manufacture of pure chemicals. manufacture of pure chemicals. Example, if you need sodium hydroxide is manufactured by electrolysis, and chlorine is also being manufactured by electrolysis. If you need hydrogen, is manufactured by electrolysis of water or brine. So this gives us some of the applications of electrolysis, and this marks the end of electrolysis 1, or the effect of electric current. And this is going to form the basic part of electrolysis that is also going to be joined with the electrolysis that is under electrochemistry in Form 4 work. So that's the end of effects of electric current in Form 2 work. So this basically is on effects of electric current on molten substances only. But in more detailed one, when it comes to effects of electric current on solutions, this is going to be under electrochemistry in Form 4 work. Thank you.